In this lesson, we talk on geometry, in particular, Euclidean geometry, the Tan-chord theorem, similarity and proportionality, and a lot of topics that pertain geometry. And we're getting started right now as follows. Right, the first question. In the diagram below, ABCD is a cyclic quadrilateral. So we have A, B, C, D is a cyclic quadrilateral. A, B, and D, C are produced to meet at E. A, B, and D, C are produced to meet at E. A, D, and B, C. Right. A, D, and B, C are produced to meet at F. Right. You can see A, D, and B, C are produced to meet at the point F. And the point F is at the bottom of the diagram. Right. We furthermore have that the angle AFB equals 2x. Right. So we look at this. The angle AFB equals 2x. We're able to see the angle 2x there. Next, the angle DAB equals 3x. Right. So if you look at the angle DAB, the angle, it's exactly 3x. Moreover, we have that the angle AED equals x, the angle AED equals x, exactly. Okay, so we have that precisely, and we continue to solve this particular question because the question says determine, giving reasons, the value of x. We need to find the value of x, and the question is, to solve this particular question, where do we start? And what exactly do we do? Right, there are a couple of things we can take into account. The angle D1 can be determined with precision. It is exactly this plus that, 3x and x, which equals 4x. So we then say the angle D1 is exactly equal to 4x, right? Because how do we know that? We actually can write a bit more steps here and say the angle D1 can be seen as the 3x and x. So in other words, the angle D1 is actually 3x plus x, which equals 4x. Why is the angle D1 equal to 4x? The reason for this is because we have the exterior angle of triangle. Right, the exterior angle of triangle. So in other words, we remember what we did at grade 10. If you have here a triangle that can be drawn in this particular fashion, we have that this angle here equals this plus that. So in other words, the angle D1 is 3x plus x, right? So this is what you call the exterior angle of triangle because the exterior angle of a triangle is the sum of the interior opposite angles. Moreover, we can be in a position to determine the angle D2. Right, what is the size of the angle D2? The size of the angle D2 is 180 degrees minus 4x. Why is this the case? This refers to angles on a straight line. Angles on a straight line. Right. So we have angles on a straight line there. And because we already know that this angle is 4x, and therefore this angle here will be 180 degrees minus 4x, simply because we know that the adjacent angles on a straight line are supplementary angles, and this means the adjacent angles on a straight line, when you add them up, this together with this, added together, will yield 180 degrees. Okay, so we're good with this so far, but we have not answered the question yet, and we are building momentum, gathering facts based on the diagram that is given. We have so far used two results. The grade 10 result, the exterior angle of a triangle, equals the sum of the interior opposite angles, but also the adjacent angles on a straight line themselves are supplementary there. In other words, angles on a straight line becomes the reason that is accepted at metric level. Now, the angle B1, next. The angle B1 can be seen clearly because you can see there's a 3x and a 2x there. So we are able to see that the angle B1 is actually equal to exactly 3x, right, added to 2x. Why is this the case? 5x. The angle B1 is just going to be this plus that. Right, exterior angle of triangle. Exterior angle of triangle. So in other words, similarly,
Can it also be exterior angle of cyclic quadrilateral?
Okay, that's a good question. Yes. You can actually use the fact that you have exterior angle of cyclic quad.
So it can also be 180 minus 4x as well.
Okay, yeah. Yes, it can also be 180 minus 4x. Well done. It can be 180 minus 4x. Okay, because this equals that. So in other words, I mean, you really are on point because, yeah, thank you so much for mentioning that. So we are practicing. This question came in one of the June examinations. Okay, yeah, you're on point because we remember that if this is cyclic quad, the angle here equals the angle there, which is the exterior angle of cyclic quad. So it can actually be the same as 180 degrees minus 4x. Very well done there. But obviously, it is most certainly a very true and very correct, very accurate observation. And we move forward to the next point. Right, next, we're able to see that the angle B1, right, the angle B1 is actually equal to the angle D2. The angle B1 equals the angle D2. And well done to your observation there, Noah. In other words, we're dealing with the exterior angle of cyclic quad. Exterior angle of cyclic quad. So in other words, the exterior angle of cyclic quad is equal to the interior opposite angle. Next, what is the angle B1? What is the angle B1, but also what is the angle D2? We know that the angle B1 is actually 5x. So in the place of the angle B1, we put 5x equals the angle D2. What is the angle D2? It is 180 degrees minus 4x, because D2 is exactly that. Next, what is this? You bring the 4x to the other side, giving us 9x equals 180 degrees, which means x is 180 degrees divided by 9. And if you divide by 9, this actually equals exactly 20 degrees. What is the conclusion? The conclusion is that x is 20 degrees. X is 20 degrees. And that's the answer. So x equals 20 degrees. Any suggestion, any contribution, any remark, any different view to this? No?
It makes sense. It actually makes sense. Thank you, sir.
Okay, that's fine. We move to the next question. Once again, this discussion is recorded and you'll have a chance to play around with a couple of questions. And also, I mean, during the course of the week, we can be able to share more practice questions and more theorems. We need to remember their proofs. There are some theorems whose proofs we need to always remember in the exams. And we move to the next question right now. Right, so the next question is the following. Right, in the next question, we have a question that came in one of our June examinations at grade 12. And we have that in the diagram, TSR is a diameter. So you have that TSR is actually a diameter of the larger circle. So we have two circles here, and we can see that TSR becomes the diameter of the larger circle having center S. In other words, the point S is the center of this particular circle here. Next, chord TQ of the larger circle cuts the smaller circle at M. Right, so we're able to see that chord TQ cuts a smaller circle at the point M. PQ is a common tangent to the two circles at Q. Right, we're told that PQ is a common tangent there. But in other words, because it is a common tangent, what is a common tangent? A common tangent is a tangent to several circles. In this case, 2 circles, right? So SQ is drawn. We are able to see, therefore, that SQ has been drawn, and now it has been drawn to actually meet the tangent PQ, indeed, at the point Q, as it can be seen there. But moreover, the examiner is generous to give us more information that RP is perpendicular to PQ. So you're able to see that RP is perpendicular to PQ, and MS is parallel to QR. MS is parallel to QR. Okay, these are parallel lines, and therefore we can be able to see the rest of the alternate angles and a lot more. Proof giving reasons that SQ is the diameter of the smaller circle. First things first, we're looking at the first question, 10.1.1. We need to prove. Right, we need to prove that SQ is a diameter of the smaller circle. So in other words, here it's S and there is Q. If you want to prove that it is a diameter of the smaller circle, what one thing actually would be necessary to do? You'd have to prove that. How do you show a diameter? How do you prove that a chord in a circle is a diameter? It must subtend an angle of 90 degrees at circumference. If ever we can be able to show that SQ subtends an angle of 90 degrees at the circumference of the circle, we will be done. Right, so, and that is what we need to do. And it is certainly one thing that we can do. But now, what exactly and how can this be established? Right, we pay particular attention at this point as we reason very cautiously. What did the examiner tell us? So one way to prove that this angle is 90 degrees, because once we are able to establish that the angle M2 is 90 degrees, that will mean SQ is the diameter. How do we prove that the angle M2 is 90 degrees? We need to look for another angle that is 90 in the diagram. So in other words, can we be able to find a diameter? Yes, S is the center of the bigger circle, and therefore a line that passes through the center of the circle is called a diameter. Right, so in other words, that means that TR is the diameter. If TR is the diameter, we know that a diameter to a circle subtends an angle of 90 degrees at the circumference of the circle, meaning this particular angle here is actually exactly 90 degrees. Right, so, and that is what we're going to say, and that is what we're going to say. And we then say, Mr. Examiner, we are excited to write the following in our attempt to prove this. So we then say the angle Q1 plus the angle Q2 is equal to 90 degrees. The angle Q1 plus the angle Q2 is 90 degrees. Why? Why? Because it is an angle in semicircle. It is an angle in semicircle. Because an angle in semicircle, an angle subtended by a diameter. How do we know that TR is a diameter? TR is a diameter because we are able to see that if we look at this particular formation here, okay, this is indeed, TR is indeed a diameter, and therefore it subtends an angle of 90 degrees at the circumference of the circle, meaning Q1 plus Q2 equals 90 degrees. Okay, we're good with that. Let us move on to the next point. Now, what then is next for us to establish here? So once we know that this angle is 90 degrees, we need to move this angle to the angle M2. We need to relate these so that if this is 90, does it mean M2 is also 90? Because if that is the case, then we won. And we then have a victory, because we know this one is 90 degrees. Therefore, we need to deduce that M2 is 90 degrees. Right, and it's obvious. Obvious. The angle M2 is 90. The angle M2 is 90 degrees, co-interior. Co-interior. co-interior angles. Right. Why are they co-interior angles? Why is it that now if you go back to grade 10, we know the angles, if this is parallel to this, then this angle plus this angle are called co-interior angles because now the angle dot plus the angle asterisk star would be 180 degrees as long as these two lines are parallel to each other. So in other words, at this point, this will be the case, and the reason would be the MS itself is indeed parallel to QR. Let's check this. If you say MS is parallel to QR, why is MS parallel to QR? This is a given fact. Okay, so that in the end, we know that if this angle is 90 degrees, that is also 90 degrees there. What is the next thing that we need to show? Therefore, SQ is the diameter. SQ is a diameter. Why is SQ a diameter? Right, the reason is because of the converse. Right, converse angle in semi. Converse angle in semicircle. Converse angle in what? In semicircle. So we yes, no.
How do you know like how to write the reason when to use converse and the proper reason?
Okay, that's an interesting one. When do we know when to actually use the converse or what we call a proper reason? Okay, right. So which would be sort of a direct reason, right? So now we need to look at what the theorem states first. So now, in other words, what does the angle in semicircle result state? It states that first and foremost, which we say it's an angle in semicircle. So an angle in semicircle would mean that an angle subtended by diameter is a right angle. That is the one. So what do we have first? We have that first we have an angle subtended by what? By a diameter. In other words, we have first a diameter that subtends an angle, and therefore that angle is a right angle. So in other words, we have a diameter. Right, if you have a diameter, and this diameter produces 90 degrees. Right, and therefore it becomes therefore the direct one. So you have a diameter, and the diameter subtends an angle of 90 degrees there. The converse would be, now you are seeing an angle of 90 degrees. What does it mean about the chord that subtends that angle? So in other words, here we first have been able to establish that this angle M2 is 90 degrees. Then we want to know if what can be said about this chord that is said that it subtends or it spans. It spans this angle of 90 degrees. What do we say about this chord then? Because now the first thing we have is the angle of 90 degrees. So we're starting from the end, and therefore we're moving in the opposite direction, and hence the converse. So if an angle of 90 degrees, then it means the chord must be a diameter. And hence that becomes therefore the converse, because we started with the angle M2, and then we then said, if the angle M2 is there, we want to know and want to deduce something about the SQ, and we're able to see that indeed SQ will be exactly 90, would be exactly a diameter. It's a special type of chord because a diameter is a chord that passes through the center of the circle. Any idea? Yes, no.
So converse means opposite.
Yes, converse means the opposite. Well, it would mean the reverse. Yeah, it would mean the reverse, which you could right. Okay,
so like
okay.
if you see a 90 degrees and then you like, therefore that chord is a diameter, then you say converse.
Yes, definitely. Then you say converse. If you say converse, if you look at the reverse statement, what is the forward statement? The forward statement, or what you could call the standard result, is to say if you have a diameter, a diameter, then it subtends an angle of 90 degrees at circumference. If you have an angle of 90 degrees at circumference, then it must subtend what? Then it must it must actually, therefore, if you have an angle of 90 degrees, therefore this angle of 90 degrees is such that it is subtended by a diameter. And obviously the fact that now we're starting with an angle and moving back to the diameter, and therefore obviously this means it is the converse. By in mathematics, converse, it means the result, means the reverse statement, because now if you then say there's a statement P implies Q, then what would the converse be? And P implies Q it's a normal direct implication, and therefore you'd look at the converse. What is the converse? The converse would be Q implies P. That would be the converse. Q implies P. That would be the converse. So now, I'm actually trying to obviously sort of elaborate on the notion of the converse, and so the converse becomes sort of the reverse statement. You start from the conclusion. Okay, you start from the conclusion, and you actually end up with what you call the premise. Okay, the premise, whatever we start with, and this becomes what we call the converse. I mean, we can have examples of, you know, that makes sense. Like, what would this be the case? P implies Q, right? P implies Q would be that, for example, every person who is tall, or every person who is 18 years old is at matric level, at least. Right. So now you can then say every 18-year-old is in matric. Right. So in other words, that's an example of really saying if somebody is 18, then they are in matric. What would the converse of that one be, of that statement? If somebody is 18 years old, then they're in matric. Now, if you look at the reverse of that, the converse of that would be that if somebody is, okay, let me write that clearly. I want us to just look at these examples, because you're going to be seeing this a lot at university when you're doing computer science and mathematics. So it's taught in mathematics. Okay, so this is under logical reasoning and mathematical logic, propositional logic, we call it. So if a learner is 18 years old, this implies that the learner is at grade 12. Implies that the learner is at grade 12. What would the converse of that be? If a learner is 18 years old, then is at grade 12. Now, let's look at the opposite of that. What would the opposite of that one be? So the opposite of that one would be if the learner, which is, I mean, the converse of that is the correct word to use. The converse is we start from the conclusion to the premise, and by saying if a learner is at grade 12, then they're 18 years old. Okay, then they're 18 years old. Okay, I mean, these things might not be true sometimes. It might not be true because you can find that you can't say if a learner is 18 years old, then it's matric. It's at matric. Well, because, I mean, age is just a number. You know, the some learners are younger than 18, some are over 18. So it's just so it's either true for some, it's not true for some learners. Okay, right. So we're good. So yeah, we continue to the next question. Right, moving to the next point. Right, so now let's move to the next point. The next point is 10.1.2. 10.1.2, we need to prove that RT is equal to RQ squared divided by RP. Okay, let us prove this one. The question is, how do we even prove this one here? We need to prove that at this point, whenever you have, this is R, and that is T, we need to prove that RT squared right, or rather RT is equal to RQ squared divided by RP. Let us prove these together. How do we prove these together? So we're going to decide here, and this is how we do this. So we decide to work in several triangles. So we're going to say in triangle, right? First things first, in triangle, we choose any triangle that works. So you need to look at this very carefully. What size are we mentioning? We're mentioning RT, but we're also mentioning RQ. And then we're also mentioning, right, so if you have RT, let's check, RT is this one. And then now you also have RP, or rather RQ. And then there's also RP. RP, this one. RP is this one. So now we're going to say we're going to work in the following triangles. In triangle, RTQ. In triangle, RQP. So we're going to work in triangle, RTQ. Why? Because we can see there's RT here, RT, and then there's also RQ, but there's also RP. Now the RP means that the RP is part of the triangle RQP. We're good. So we want to prove this particular statement. Let's proceed to prove this particular statement. And we actually start as follows. Now, first things first, if you look at the triangle RTQ, RTQ, can we be able to make an observation here? Like, if you're able to see this angle here, because we have a tangent, this angle there, it's like we are seeing something like this from grade 11. We're seeing something like this. So this must be this, as long as we have a tangent. As long as we have what? We have a tangent. So which means that we have that the angle Q3, the angle T. Okay. T is Q3. The angle T is Q3. And that is the Tan-chord theorem. Right, so the angle Q3 is actually equal to the angle T, and the result of this is the tangent chord theorem, the Tan-chord theorem. And we proceed right now to, establish more results. And we have exactly the following to deduce. Let's move on to the next point. Right now, if we know that Q3 is equal to T, Tan-chord theorem, what is the next thing that can be established here, as a matter of fact? Because we have this one, let me just keep them marked. Let me just keep them marked in red like this with the red dots. Then now we have the triangle RTQ and the triangle RQP. We want to prove that these two triangles are similar. We want to prove this is similarity and proportionality. So we need to prove that these two triangles are equiangular. The RQP and the RTQ. We need to prove that they are equiangular. So, right, so we have the Q3 is actually angle T. Next, now we need to establish that there's an angle of 90 degrees. Like you can see, there's an angle of 90 degrees there. If we're able to find an angle of 90 degrees in this triangle here, we are winning. By good luck, this one, it's the angles, because this one is the diameter, so it subtends an angle of 90 degrees. But this triangle here already is already having what? It's already having the angle of 90 degrees. So in other words, the angle Q1, right, the angle Q1 plus the angle Q2 is 90 degrees. Why? Co-interior. Co-interior angles. Right, so we know that the angle Q1 plus Q2 is actually equal to 90 degrees. Why is this the case? Right, so I mean, we can already state that, but I feel that the best would be to say angle in semicircle. Would be to say angle in semicircle, because we already have that the big circle has center S, and therefore R is a what? It's a diameter. It's a diameter. So we have that we have an angle in semi. Angle in semicircle. Angle in semicircle. All right. Okay, if this one is 90 degrees, right, this one is 90 degrees, and also this one is 90 degrees. Okay, so now we therefore have one. Once you prove that you want to actually establish that two triangles are similar, two triangles are equiangular or have equal angles, you just need to establish two angles that are equal, then the third angles become automatically the same. So now, because of that, we're only left with this angle here, R1, and here we're only left with this angle here, the angle R2. So in other words, we're able to establish that the angle R1 is actually equal to the angle R2. Why is this the case? Because you have angles of triangle, angles of triangle. Right, because it's the third one, the third angle. Sometimes you can say third angle here. Okay, good. Now, with this, then we already know that this angle dot equals the angle dot, angle star equals angle star. 90 degrees is 90 degrees. We're good. Awesome. Awesome. So, therefore, the triangle RTQ is actually similar to triangle RQP. So the triangle RTQ is actually similar to triangle RQP. Why is this the case? Why is this the case? We must give the reason why this is the case. Well, the reason for that, it is angle, 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 angle. Okay, awesome. Okay, now this must be always written in order. Like we know that in the triangle, so R is equal to R. In the triangle RTQ, R is equal to R. And then we have that the angle T is equal to the angle Q. T is equal to Q. In the RTQ, the angle Q is equal to P. The angle Q is equal to P. Okay, now, which means RT divided by RQ. RT, now you divide, so yeah, something like this. So you map this one with this one. So you have that the RT over RQ is equal, okay, because these things have been written in order, so you can just be able to write the proportionality from the similarity of the triangles. Right, so now you're able to say RT over RQ is equal to, then you can be able to take something else. Right, and then you can be able to take, for instance, TQ. You have taken the first ones, you can take these ones. Right, and taking those, it means that you'd have, for example, TQ over QP. And then you have this with that. Right, so you can take, for example, RQ over RP. Okay, therefore we have this. We have this. Okay, now we need to choose here. We need to choose. What do we choose? We choose exactly the parts of this equation that will produce this. For example, there is RT. So we can take this one. And then now, if you take this one has RQ. and RP. So you take that one. So it means that you'd have, therefore, as a consequence, the following. So it means that we have RT over RQ, which equals RQ over RP, and this is RT is equal to, you cross multiply so that you have RQ by RQ, which is RQ squared, you divide by RP, and therefore this is exactly the answer, and we've been able to prove this one here. Any question, any suggestion, anything to add or remove there? No, but yeah, we have been able to prove these in some detail. Any question, remark?
No, it's fine.
It's fine. Okay, very easy. Next
Yes,
question. All right, thanks, Noah. Next question would prove the following. 10.2. And in 10.2, the question is clear. If MS is 14 units, and we're going to do it on the diagram. Right, so here we have that. MS is 14 units. So this is 14. And PQR, or rather PQ. PQ is the square root. 640. Calculate, giving reasons, the length of the radius of the circle. Calculate, giving reasons, the length of the radius of the circle. So you have this particular lengths there in units, and we want to be in a position to prove these in detail. So now this is awesome, but we go back to grade 10 because now we're dealing with this, but we actually have that this is like at the center, and therefore a line drawn from the center to circumference is called a radius. So this is going to be a radius, and that's going to be a radius, but radii are equal. Radii are equal to each other, and therefore we're good. So which means that we can be able to determine this and that. But also, if this is the case and this is parallel to that, we can be able to make more deductions. Okay, now we're looking at 10.2. Now, it means the actual QR equals, QR is on here, is 2 times 14. And the reason is the midpoint. Midpoint theorem. Midpoint theorem. Right, grade 10 is the midpoint theorem because this S is the midpoint. It's like the center of the circle, and therefore it generates whatever we have there. So in grade 10, we're taught the midpoint theorem. What does the midpoint theorem say? The midpoint theorem in grade 10 says if you have a line segment that joins the midpoint of two sides of a triangle, it is parallel to the third side, but also it is equal to half the third side. So in other words, this one here is half of this. But now if we want to get the QR, it means this QR is so long, it is equal to 2 times the short one. 2 times the short one. Okay, this is the midpoint theorem because of the center. They're from grade 10. So now, which means that our QR is 28. It's 28 units. 28 units. We want something else. Okay, so we're able to get the following. So let us put it on the diagram, and we have the following. So this one here is actually 28 units. So we have that QR is 28 units. Next, we want to determine more things. And now we remember, we want to find the length of the radius of the larger circle. Okay, the radius of the larger circle. So we can be able to find the radius, meaning we can be able to find like TS, SR. Let's find RP. RP. Oh, okay, because we already know this one and this one. So now you have exactly this here. We have exactly this. 28, the square root of 640. And then now this is R, and this is P, and this is 90 degrees, and this is Q. What do we want to find? We want to find, for instance, we can be able to get RP, for example. First things first. Right, so we can use Pythagoras theorem in this triangle because it's a right angle triangle, and therefore we can then say, Mr. Examiner, in triangle. Often state the triangle in which you're working to make sure that the examiner does not find you at fault. In triangle RQP, so now you actually therefore need to then say 28 squared. Right, so in this triangle here, we have 28 squared, which is the hypotenuse is RP squared plus the square root of 640, like this, which is 28 squared minus 640, which is RP squared. Okay, let's do this. RP squared is 28 squared minus 640. What is the answer? Okay, you get 144. You get exactly 144. Can always check with the calculator here. Can always check with the calculator. Right, can always check with the calculator and do some practice and be in a position to do the following. Right, so we're effectively saying, for example, if you have this, you have 28 squared, and you minus 28 squared minus 640, minus 640, and the result is 144. We're good. Okay, with that mentioned, we want to get RP squared, which is 144 square root, which means that we have RP, and then obviously you take the square root, but it's positive length, and the square root of 144 is actually exactly 12. It's 12 units. Right, so we have that the RP itself is actually 12. It's actually 12 units. What is the meaning of this? What is the meaning of this? We're interested in RT. RT is RQ squared divided by RP. So what is RT? Right. So we continue. We continue. So that in the end then, if we have that this is the case, what is RQ in this formula? Because we're able to see that if we get RT, then we can just divide we can be able to, okay, RT itself, what would RT be? Right, so RT itself is the diameter. So once you get RT, then you can be able to get the radius. So what is RQ? RQ. Right, so we have this, which is RT equals RQ squared over RP. What is RQ? Right, so your RQ is 28 squared. RP, 12, which means RT equals, you square these things. You square these things. And now when you square these, simplify, you'll get actually 196 divided by 3. 196 divided by what? Divided by 3. And with this mentioned, then we have exactly the following fact. So now this RT represents what? This RT is a line through the center of the circle, which we call a diameter. So the diameter is exactly that. Now we then need the radius. The radius, which is RT out of 2. Half RT, which is 196 out of 3. What is half of this? It's 98 out of 3 units. It's 98 out of 3 units, which is the radius. So the radius becomes the diameter divided by 2, and it becomes 1/2 of the diameter. What is the diameter? The diameter is 196 out of 3. But if you divide 196 by 2, you get actually 98 divided by 3 units. What is this? This 98 out of 3 is the radius. the radius is half the diameter. We got R T to be 196/3, and if we then say this is the diameter, we divide by 2 is the same as multiplying by 1/2, multiplying the diameter by 1/2, and therefore we're able to get 98/3 units. So we have a chance to practice similarity and proportionality, but similarity and proportionality applied to what you call circles, right? And the midpoint theorem being applicable given the center of the circle and also radii that are involved, because you have the radii that remain involved here. What are the radii? This is a radius and that's a radius, and these radii are equal to each other. They are congruent radii, and obviously we have that. Any different view to this, we've calculated the length of the radius of the larger circle. The length of the radius of the larger circle, therefore, is actually 98 divided by 3 units. Any question, any remark, any contribution to here? No.
Can you please explain again 10.2?
Okay, let's look at 10.2. Now, in 10.2, the objective that drives us is what we want to calculate, and we want to calculate the length of the radius of the largest circle. Right, so the largest circle is this one, and we're able to see that there is a radius. A radius is a line segment from the center, like TS is a radius, and also SR becomes a what? A radius. So that in the end then, whatever we get here is the following. All right, so we are able to see that one of the easiest ways, there are many ways, of course, one of the easiest ways is to find RT, because we've already got a formula for RT. Normally, it helps to always look above. Now, we know that we have already got RT, and we're able to see, okay, we actually can get RT using this particular formula, but now this formula has RQ and RP. So if we're able to get RT, we would have got the diameter, and therefore the diameter can be divided by 2, and then would get the radius of the larger circle, and we're done. Now, what is RQ? We look at this and be like, okay, the examiner gave us that MS is 14, and then now we would wish to get RQ, but if MS is 14, then what do? We think, okay, we can use the 14 to get this one, but how to use the 14 to get the RQ? And one way to do that is to immediately say, the best we can do is to then say there is a midpoint. This S, it's like the midpoint of TR. It's like a midpoint. It's a midpoint. If this becomes a midpoint, then you can use the midpoint theorem, grade 10. Grade 10 midpoint theorem. Right, so if this is the midpoint, it means that for the TS equals exactly SR. It means that TS equals SR. Right, if this is the case, then we have the following. So now we can be able to then say, the midpoint theorem says that this short one, if this particular point S is the midpoint, this short one is such that in length, if you compare the two lengths, we say a line segment joining the midpoints, because if it joins the midpoint and is parallel, then it means that this is also the midpoint here. So a line segment joining the midpoint of two sides of a triangle is parallel to the third side of the triangle and equals half the third side. So this is half the third side. Now, if this one is 1/2 the third side, it means therefore that if this one is 14, this one must be 28. Because if you take half of 28, you get 14. That is why we then said, okay, we can be able to get QR, and then the QR is double 14, which is the midpoint theorem. And then the QR is double 14, which is 2 times 14, which is 28 units. 28 units. Now, in the triangle RQP, you then have 28 squared is equal to RP squared plus the square root of 640. Which is 28 squared minus 640 equals to RP squared, which means RP squared is equal to 28 squared minus 144. Okay, now we got the RP. Why do we want the RP? We've already got RQ. here, and RQ is 28 squared, but we're left with the RP, and now we can see that if we have this and that, we can be able to get RP here. And then now we're able to see that, okay, if we take the square root both sides, then RP is 12. Then RQ we know it's 28. RQ is 28, and then RP is 12, and you simplify 196 out of 3. 196 out of 3. Okay. Now, we have already got, if you divide these 28 squared by 12, and then we are able to get 196 out of 3, then it means we have RT. And then now we got RT, and this RT is the diameter of the circle, and we want the radius. So we need like half of it. So we're going to take half of the diameter is the radius, so it's half of RT. We divide RT by 2, which is half of 196 out of 3. Then we divide 196 by 2, we get 98 out of 3, which is the actual radius. So we got that the radius is 98 out of 3 units there. Anything to add or remove there, Noah?
It's fine, thank you.
All right, good. Right, we're moving on, and we're trying more questions. And let's try the next question. Right, the next question is this one. Very nice and easy. In the diagram, we have the following. Right, in the diagram, we have the following. MP is the diameter of a circle. MP, the diameter. These examiners love diameters because it's a diameter. It must obtain an angle of how many degrees there? An angle of 90 degrees. They've not asked us, but it's already obvious. Right. Now, yeah, it is in the diagram, the MP, the diameter of a circle centered at O. MP cuts the chord NR. Right. At T, there's T. Radius NO. Radius NO and chords PR. In chords PR, MN and MR are drawn. The angle R1 is 69 degrees. Okay, we're able to see the angle R1 is 69 degrees. Determine, giving reason, the size of the angle R2. Very obvious. The size of the angle R2 is pretty obvious. Sometimes I'm going to give you a chance. I know I'm not.
It's 21.
It's 21. Why is it 21, Noah?
90 minus 69.
90 minus 69 degrees. Why 90? So an student can be like, why is the 90 there?
Because it's angled in a semicircle.
Angle in semicircle. Very, very well done there, Noah. So we proceed. So now we're able to see that this is going to be exactly 21 degrees. And the reason for this, we have angle in semicircle. Angle in semicircle. Angle in semicircle. Right, so we're good. Right, the next question. Right, then we have the first question. Right. So we move to the next point. Right, move to the next point. The angle O1 is the next subject of discussion. The angle O1 is the next question that we're discussing. What do you think the angle O1 is, Noah? Just practicing, then we're going to discuss, of course. But we're just getting
138.
You think it's 138 degrees. Okay, that's awesome. And Noah thinks that it is actually exactly that one there. It is actually exactly 138 degrees. Right, let's check that one. We're going to check it together. So if you're looking at the angle O1, it is this one. Why do you think that's the case? I mean, your answer is on point. Why?
Angle at center is twice.
Yes, the angle at center is twice the angle at center. So now we go back and we remember that if we have a diagram like this, the angle at center is twice angle at circumference. If this one is 69 degrees, then this will have the angle at center. So which means, therefore, at this point, we are sure, but most certainly very, very confident about the fact that whenever you have this particular angle O1, it is actually an angle at center, which is 2 times 69 degrees. And this means that we have angle at center. Angle at center equals 2 times angle at circumference. Angle at circumference. Right, so we're good. What is the next point? So we continue right now and try the next question. That's okay. That's okay. Right, so we try the next question and we have most certainly the following point. We have most certainly the following points. Right, so which means that the angle O1 is 2 by 69, which is 138 degrees. Right. Okay, so we continue. Right. Now, if this is the case, then angle at center is 2 times angle at circumference. Okay, so yeah, this one you're able to get. So I'm not gonna bother you in terms of whether you understand it or not. I'm just assuming it's obvious. Okay, the next question is the angle M1. This is M, but we want this one. What is the size of this? What is the size of this? We want the size of the angle M1. What's the size of this angle M1? What's the size?
21. 21.
21. Okay. Right. Wow. That's awesome, awesome news. And you can see that, you know, you're doing a brilliant job because this one is 21 degrees and you're able to see that this is 21 degrees. And these types of angles are awesome angles. And these are the kinds of angles that deal with the butterfly. They deal with the butterfly. So an angle that sits here will be an angle that sits there. And these angles are angles in the same segment. In other words, we're able to see that the angle M1 equals 21 degrees. Yeah, and so these are angles in the same segment. Angles in same segment. Angles in same segment. Right, angles in same segment. So that is actually the answer there. I'm excited that you're able to see that the angle, this angle star equals this angle star, etc., etc. And therefore we continue to solve even more questions. We continue to solve even more questions. So we have therefore that the angle M1, which is actually 21 degrees, is indeed an angle, right? And this has to do with angles in same segment. In other words, the angles in same segment are equal to each other. Next point. The angle M2. The angle M2. Let's look at that one. Okay, we've already seen that now already saw that this one is actually 21 degrees. Right, and we have that. So we continue. We continue. So at this point, we have exactly the following. We have exactly the following. Now, the couple of things you've already seen that this one is also 21 degrees there. But now, we want M2. This one. There. Okay, M2 must be determined if it is further given that NO is parallel to PR. Let's check this one. So we have that NO is parallel to PR. Like this. NO is parallel to PR. Okay, if these are parallel, what then are we able to establish here at this point? But how do we use that to be able to find the angle M2? This one, the angle M2. This is what we want. Right, it's exactly what we desire. And therefore, it is really very, very awesome. Let us solve this particular question. Then the thing is, what then are we able to achieve here, right, at this point? And how can we be able to determine the size of the angle M2. So we reason and think very, very carefully. But the question is, how do we do this? We want to find the angle M2, but what is the size of the angle M2? Right, so we need to think.
So
We surely need to think. Yep, what do you think?
so for O2, you're gonna first find O2, which
But
is
I'm
gonna
going to
be
find the angle
180.
O2, which is what? What do you think?
180 minus 138. Then
180
you get
minus 138,
42.
because you know that this one is 138, so you can use 180 minus exactly that. Right. So in other words, you really can say O2 is 180 degrees minus 138 degrees. And what are we getting? We're getting actually a 42 degrees. And the reason for this is that you have angles on a straight line. Angles on a straight line. Next.
Then therefore P is gonna be 42 as well because of
Right,
alternating
so you're able to
angles.
see that this one is 42 degrees, and we're able to see that the angle P is also the same as 42 degrees because these are alternate angles. Excellent move there, Noah. Right, so which means the angle P is actually 42 degrees. Why is this the case? Because these form a Z, and these are alternate angles. And the reason for this is you have NO is parallel to PR. NO is parallel to PR. Okay. Then we got that this one is 42 and that is 42. And then we're done. What is then the
Yes,
size
and
of the angle M2?
then you just say M2 is 180 minus
180 minus the rest of the angles in this triangle. So in other
minus
words, yeah.
minus 90 minus
Yeah.
90 minus 42, which
Wow,
is gonna
that's
be
awesome,
48.
awesome. Because this whole angle here, it's 90 degrees, and then you say 90 degrees, and then here you say minus 42. And these are what?
It's sum of
Sum of
angles in
angles.
triangle.
Sum of angles in triangle. What is angle M2? 48. If you subtract
48.
everything, you get 48. You know, because if you subtract the 180 minus 90, you get exactly a 90. And 90 minus 42 is 48. And therefore, we are done. We are done. We are done. Right, so we're done. Any question? No question. I would imagine you understand this quite well, isn't it? Right. I would imagine this, but obviously there are many other ways to do it. There are surely many other ways to actually do this particular question, and one can be in a position to find that. One can be in a position to actually find that. All right, so we continue then to prove it most certainly as follows. Right, so now the next question. The next question. Right, the next question is this particular proof here in the diagram. Right, ABC is a triangle. A, B, C is a triangle. D and E are points on sides A, B, and AC. So you have D and E certainly are points on A, B, and AC respectively, such that DE is parallel to BC. DE is parallel to BC. Use the diagram right above to prove the theorem, which states that a line drawn parallel to one side of a triangle divides the other two sides proportionally. That is proof that AD over DB is equal to AE over EC. So we have the following. We have the following. Right, so now it's then very interesting to do and very easy to prove. Right, so now the couple of things you need to take obviously into account. Right, so now to actually be in a position to establish this, we are able to do the following. Right, we're able to achieve the following. And we proceed as follows. We proceed most certainly as follows here. How do we prove this? We need to prove that. So we're required to prove that AD over DB is equal to AE over EC. And how do we ever prove that? AD over DB is AE over EC. Okay, we're practicing this proof because it's very examinable. Now, these proofs are like very important because you must like, know them for exam purposes. We actually gonna do a construction. Right, we're gonna do a construction. So as we do the construction, what you then do, you join BE and CD, right? So what you do is you're gonna first join BE, and also you're gonna join CD as follows. Join like so, and also join these like so. Okay, so you join BE and CD and draw. And draw H1. H1 from E perpendicular to AD. Right, then you draw H1 from E perpendicular to AD as follows. And this now is what you call height 1, H1. And H2 from D perpendicular to AE. So we're going to actually construct another height like this. You need to learn this even in the prelims. These things are there. In the finals, these things are there. Right. So how do you learn proofs in mathematics? You like repeat and repeat and repeat and repeat and repeat and repeat. Right. So until you were able to like remember the proof, okay, because it's a proof, so you must like learn it as it is. Right. So now we're good. Let's look at the proof now. Right. We're looking at the proof. What is then the proof? To look at the proof, then you look at the area. Triangle ADE. Okay, so area triangle ADE, area triangle BDE, okay, area triangle ADE divided by area of triangle BDE. Now the area of triangle ADE is actually half the base, right? Dealing with the ADE, the base, you can choose the base, AD, multiplied by the height, H1, divided by the area of the triangle BDE is half the base. Choose the base, BD times the height, H1, and this is AD over BD, like this. Next, you're gonna actually be in a position to establish area triangle ADE, area triangle DEC, half. So now at this point, okay, we are dealing with this side now because we dealt with this side, the AD and the BD already been achieved here. And then now we are dealing with the AE and EC. So now if you look at the triangle ADE, then we have half the base, which is AE multiplied by the height, and the height is height 2, divided by half the base which is actually EC for the triangle DEC, triangle DEC. So you're taking half the base, which is exactly EC, multiplied by the height. The height is this one, H2, right? You're going to take H2, and therefore H2 cancels, 1/2 cancels, giving us AE over EC, like so. Right, so we have the AE over EC, we have AD over DB. What then is the next thing to prove here? What then is the next thing to prove here? And then we have area. Triangle ADE equals area. Triangle ADE, which is common. Common. Right, the area of the triangle ADE perceived with base AD is equal to the area of the same triangle. ADE is equal to itself, perceived with the base AE. So we have the base AD and the base AE, and these are the triangle ADE is equal to itself in area terms. And now we continue to then say, but area triangle BDE is equal to area triangle DEC, which is actually the reason for this. So we're dealing with the bases now. We're dealing with the BDE and also with the DEC as triangles. And therefore, this is the case because of the same base. These triangles have the same base, and also they have the same height. They have the same base. They have the same base and height. They have the same base and height. DE is parallel to BC. DE is parallel to BC. Right, so we have this. So the numerator is the same as the numerator. ADE is ADE in area. BDE is DEC in area terms. So now, what then are we able to state out of this? Right, and we're able to make the following conclusion. We're able to make the following conclusion as follows. Right, so we're able to then say, if this is the case, then we can take the area. The area of triangle ADE over the area of triangle BDE. These areas are equal, so that this is the area triangle ADE divided by the area triangle DEC, like this. So yeah, it means therefore, because the numerator here is the same as the numerator, the denominator is the same as the denominator, it means that this whole thing here is equal to this entire thing there. And as a consequence, we're able to see therefore that the area triangle ADE over BDE area is actually the same as AD over BD, like so. And this other one on the right, ADE, DEC, is AE over EC. AE over EC. All right. And this is the proof. And with this proof, we are done. Any question on this theorem? All right, this theorem is very, very important. And if you prove this theorem correctly, you are able to get exactly 6 points. So it's a very, very important theorem in the exam. So you're able to get 6 points or just 6 marks. Any question, any remark, anything to add, remove from this, Noah?
It's fine.
All right, good. We move to the next point. We need to practice these and repeat, and until you understand it. Okay, we move more to similarity and proportionality. In the diagram, M is the center of the circle. M is here. It's the center of the circle. It's like a dot that is on the other side of the chord AB, and you really can see that it's not on the chord. A, B, and C are points on the circle. A, B, and C are points on the circle so that AC is equal to BC. AC is equal to BC. PA is the tangent to the circle. Right, PA is the tangent to the circle at the point A. There it is. But PQ is drawn parallel to CA. Let's check. Right, we have PQ is drawn, but it is parallel to CA. You can see the parallel markings there. Right, so we go on. We proceed and we do this particular question with so much ease. Right. So we continue. Right. So we continue. Right. So right. So now at this point, right. So you then say P is a tangent to the circle at A. PQ is drawn parallel to CA. So you have that PQ is drawn parallel to CA. To meet BA produced at Q, you have the point Q. BC produced meets PQ at R. Right. So you have exactly BC produced, right, meets PQ at the point R. Okay. And we have the following here. Right. So yeah. Okay, at R. And AR is drawn. Right. So we can see that AR is drawn. Here is the line segment AR. Let the angle Q be X. Okay, there it is. The angle Q is X, and you can see it over there. Determine, we're looking at 9.2.1, determine giving reasons for other angles each equal to X. Very popular question in the examinations. Determine 4 other angles each equal to X. So there are several angles that are equal to X, but determine 4 of them. We start. Which one do you think, Never? Anything? Because you already know that this is parallel to this, or you can be able to go back to grade 10 and see F like this. Right. So we continue.
It's equal to
yes.
A1.
Equal to
A1 is
A1.
X.
Yeah, it's equal to A1. Why? Because you
corresponding.
Right, yeah, corresponding angles. Corresponding angles. Well done there, Never. So we're able to see that first things first. Right, the angle A1. The angle A1 equals X. Why is the angle A1 equal to X? Why? Once again, you already gave the reason. You said these are corresponding angles, which is PQ is parallel to what? PQ is parallel to CA. PQ is parallel to CA. Right, so because we already know that PQ is parallel to CA, therefore we have the result. What is the next thing here?
Then
yeah, but this is just one of the angles. Sorry, A1 is X, but so in other words, you know that this one is X. What else is X? Now we think.
B.
Well done. Okay, I can see that Never is so much on fire. Right, so B is X as well. Why would you think B is X? Because I agree with you, but why?
Because AC is equals to BC.
Because AC equals BC. So because AC equals BC, right? Or you can actually say that angles opposite Angles opposite equal.
Equal sides.
Equal sides. Well done. Angles opposite equal sides. Or you can go on to say these are base angles of an isosceles triangle, because if two sides are equal in a triangle, then we have what we call an isosceles triangle. Okay, that has given us this is x, and that is also x. But the examiner is saying, hang on, there are 4. Right. Okay, so we're good.
4.
Okay, so now the examiner is saying, please. Right, so we continue. So then the point is, the examiner is saying, hang on, there are more. There are more.
Mm.
Okay, so we need to search. We need to search. Right, so now, because we are searching, searching. So the examiner is saying, please. They're actually, the examiner is saying, they just need 4 others. And I agree with Nero. The ones they've given are correct. But the examiner is saying, please, but they're much more than that. They're much more than that. But now, which other angle is there? Okay, there's a tangent that is involved here. What is the tangent? PA is tangent to the circle at A. So if this is
So
and that is A, yeah, so what do you think? Then
A2 is X.
A2, well done.
Okay.
A2 is also X. Why is this the case? A2 is also X. Why is this the case? Because of the Tan-chord theorem. Well done. I'm excited that you're able to see this one here is the Tan-chord theorem. Right, this is the Tan-chord theorem. Next point is the Tan-chord theorem. Next point. Right, so now A2 is also X. So A2 is also X because of the Tan-chord theorem. But the examiner is saying, hey, we're not done yet. They want 4, and we've like listed 3 of them. So there is one angle that is still hiding. Has not been stated yet.
P.
Well done, well done, well done, very well done. So you're able to see that the angle P itself, because this is part of this, so it's alternate. The angle P is X. Why is the angle P X? Alternate angles. Why is this? Because they're parallel lines. What are the parallel lines, Nero? PQ is parallel to CA.
PQ and A.
PQ is parallel to CA. You agree?
Yes.
PQ is actually parallel to CA. So now with this, then you're able to see that your PQ is parallel to CA, and therefore we have that this angle P is also X there. So we've found 1, 2, 3, 4. We have found 4 angles, each equal to X, and we're done. We proceed to the next question, and the next question is 9.2.2. You need to prove that the ABPR is a cyclic quadrilateral. Let's take a look at this. A, B, P, R is a cyclic quadrilateral, and this is obvious. It is obvious. Why? Because you've already marked the rest of these angles. X, 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 X. Okay, let's move to the next. So you already found X here. You found X there. The A2 is X there. The P is X, like this.
Oh, yeah.
Now, with this, then, the examiner is saying, prove that A, B, P, R is a cyclic quad. We're already seeing what do you call a bow tie here. So it's obvious now. It becomes therefore the converse. The converse of the bow tie result, angles in the same segment result. So this equals this. Okay, if this equals that, then we have the bow tie result. Bow tie result. Bow tie result. So what then is the case here? Okay, your
B equals to P.
B equals P. Well done. So we're able to see that the angle B is equal to the angle P. Right. Why is this the case? Because they're both equal to X, and that has been proved in exactly 9.2.1 above. Next. Next. Therefore, okay, we have that the b equals p because they're both equal to x, and we proved it in 9.2.1 above. Then what is then the conclusion here? The conclusion is therefore that A, B, okay, we're going to take a look at these. P and R are concyclic. Are concyclic. Okay, let's take a look at these. Are concyclic. Now, we're then saying A, B, P, and R are concyclic. That is therefore the conclusion. And with that, we're able to say, therefore, ABPR is a cyclic quadrilateral. Why is this the case? It's a cyclic quadrilateral. Right, it's a cyclic quadrilateral. Why is this the case? Why is it a cyclic quadrilateral? We need the reason. We need the reason.
Angles
we can see. Okay. Yes, quadrilateral. Okay. Right. So what is the reason, Neo? Neo can see the reason. It is the converse. It is the converse angles in the same segment. So it is the converse of angles in the same segment because now
okay, so you said that converse, you say you use converse when you like say it in reverse.
In reverse,
right?
when you study it like in reverse, yes. When you study it like in reverse, then it's the converse. So at this point, normally, how do we state the angles in the same segment theorem statement?
Because we're proving that ABPR is a cyclic quadrilateral.
Yes, definitely. So we're proving that, yeah.
Because B is equals to P.
Yeah, because B equals P.
Then you're gonna say converse.
Yeah, definitely. Because now we have first equal angles. Right, because now in general, it's when you study it in reverse. So, but first here, what do we have first? First, we must have a circle. Yes. First, we must have a circle, and then we must have angles in the same segment. And then if the angles are in the same segment, then they're equal. So now here we're starting with the equal angles. Starting with the equal angles, and we're then saying if the angles are equal, then there's a circle.
It's a circle, yeah.
Yes. So we start with a circle, and then we have the angles that are equal to each other. Okay, like we have a circle here and the angles that are formed, of course. And then we then say if we have a circle and we have angles in the circumference, right? We have a circle and we have angles in the circumference. Right. So if we have a circle and angles in the circumference, then the angles are equal. But now, obviously, this is how we state it. But now we're saying the angles are equal. We're starting with from the end, and we're setting it like in reverse, and we're saying here the angles that are equal. Then what does it mean if the angles are equal to each other? Then it means we must have a circle somehow. So in other words, we must have that the A, B, P, and R are concyclic. Concyclic means that they lie on the circumference of a circle. Because if the angles are like the angles that are like in the butterfly are equal, angles in the bow tie are equal, right? So the angles in the bow tie. So if the angles in the bow tie are equal to each other, then it means that the points must lie on the circle. How do you say that? So yeah, you can even say, therefore, it means that A, B, P, and R lie on the circumference of a circle. But a much smarter way to state that in geometry is to say A, B, P, and R are concyclic. Concyclic means that they lie on the circumference of a circle. If they lie on the circumference of a circle, therefore, the ABPR is a cyclic quadrilateral. It means the ABPR is a cyclic quad. And we're done. Any question? Right. So in other words, why is it a cyclic quad? Because of the converse angles in the same segment. How is it the converseness? Because we are just seeing the equal angles, and seeing equal angles, then we want to deduce that, hang on, it means therefore there must be a circle that runs through. As much as there's no circle that is visible running through P, running through R, running through A, running through B, but it must be there. Why? because we can see angles in the same segment that are equal. So ABPR is a cyclic quad, which is the converse angles in the same segment result. Right. Any suggestion, question now? Anything to add or remove here?
I understand.
Okay, good. Let's move to the next point. Next point. Right, so now we have done 9.2.1, we have done 9.2.2. We are actually right now doing 9.2.3. And in 9.2.3, we must prove, right? We need to prove that BA, BQ, BC, QR. We must prove this, that BA over BQ is equal to BC over QR. How do we even start? Where do we start? Where do we begin?
Similarity.
Yeah, similarity. Well done.
You have
Similarity.
to find
So,
the triangle.
yes, we need to find a triangle that is actually very much involved in this case. And so how do we therefore proceed to actually prove this particular result? Okay, for example, what are we able to see here? We're able to see that AC is parallel to what? Is parallel to QP. Q, P, A, C are parallel to each other. Okay, if these are parallel to each other, we actually have a couple of observations to make. Because you have a line that is parallel to this, then we can be able to state these with ease. So there is obviously much simplicity in proving this. So the easiest way to do this in this exam was to just say, prove that. There was just nothing to prove here. The examiner was being funny here because it was very, very easy. But the easiest way to do this was to say BA. BA over BQ. The first. BA. BA over BQ. BA over BQ must be equal to BC over what? Okay, BA over BQ. So you're taking BA like these over BQ like these must be equal to BC over BR. How close are we to the result? We're very close, but it's just a QR there. And the reason for this is we say it is the proportionality theorem. Proportionality theorem. AC parallel to QP. AC parallel to QP. Right, so we're good. But now we close, but there's BQ in what we need to prove. There's BA, BQ, and then there's BC. Where's QR? There's BR, and then in the place of BR, we must put QR. Once we put QR in the place of BR, then we're done. Right? So now what then is it? So now it means that somehow, somewhere, somehow, it must follow that actually BR is equal to QR. Let's check QR. QR and then BR. Right, so these two must somehow be equal to each other. Yes, because this is X and that is X, and therefore this triangle here is isosceles. Okay, because this one is X and that one is X. So it means that this side must be equal to the whole side there. So in other words, this is what we have been able to establish. Right, so which means that, but QR is equal to BR. But QR is equal to BR. Why? Because these are sides opposite equal angles. Sides opposite equal angles. Therefore, now in this case, the BR is already QR, so which means therefore you have BA over BQ This is actually BC over QR. In the place of BR, we put QR because BR and QR are equal to each other, and then we're done. And then we're done. Right. So, any question on these now? But yeah, but I mean, it's not the only way to do this one. There are a couple of other ways to do it. But very often, to prove proportionality, we use equiangularity. And now this was much easier because you already had a parallel line. So we just had to obviously simply just use proportionality theorem because you already have a line that is parallel to the third side of the triangle that divides these particular sides in proportion, and therefore obviously the proportionality theorem was very immediate. But however, we can do it differently. Let's do it differently. Let's enjoy a little bit and have some fun. Okay, normally to prove this one, we decide on the triangles that we need to work in, and we use angularity. We need to prove that the angles are equal. Like in this case, because this one is like BA, and also the numerators, like BABC, BABC, the denominators are like BQ, and then you have QR, BQ, and then QR. And then obviously that suggests that we can actually decide to work in the triangle BAC and also work in the triangle BQR, for example. And then we shall be so good. Shall be so good. Right. So now I think that we need to obviously just enjoy that part and just to do this 1.2.3 using equiangularity. So, but once again, by looking at the fact that we have the BA and the BC, right, as part of a triangle, it suggests that we can decide to work in triangle. We can decide to work in triangle. If we decide to work in triangle BAC, that's another way to do the question. And also, if we actually work in triangle BAC, but we also work in the triangle, or you can call it, right, if you call it BAC and triangle, right, another triangle, what would the triangle be if you have BAC? Right, so you have the B is Q, the A is B, and the C is R. Okay, we're trying to verify the order of these, but yeah, just to obviously let us prove some of this. Right now, first things first. We want to prove that okay, we want to work in the triangle QBR and also BAC. We want to prove that these two triangles are equiangular, then we can have this. So, which is the usual way to prove it. And obviously, that will be very correct in the exam. So first things first, now we need to establish that there's an angle here that is equal to another angle, an angle in the small triangle here that is equal to the one in the big triangle. Like the angle A1, what is the angle A1 equal to? We know very well that at this point, the angle A1 is equal to x, and also the angle B is also equal to x because these are is an isosceles triangle. So which means that the angle A1 would be equal to the angle B, and that would actually be exactly x. And why would this be the case? In the exam, you would say that it has been proved in 9.2.1 above. So in other words, there's no need to start proving that again with a lot of details. But now we then have that this angle equals this. What is the next point? Angle B equals Q. Angle B equals Q. Right, so we have that this B equals Q. So we actually then right now, we are able to state the following facts. Right, so we have actually first been able to see that angle A1 is equal to B, meaning that we have an angle A1 here that is obviously equal to the angle B. But next, we're able to see that the angle B is equal to the angle Q because they are both equal to x. So the angle B is equal to the angle Q, which equals x. And this has been proved in 9.2.1 above. Right, we're able to see that here, the angle B is equal to X. Okay? Yeah, the angle B, excuse, is equal to angle Q equals X. It has been proved there. Okay, so just to emphasize, this is X so that we have the red markings. Now we have X, X, X. Awesome. Right, so now we have been able to establish how many angles? Let's check. In the triangle BAC, we picked A1. And we saw that the angle A1 was actually equal to the angle B in the big triangle. Next, we've been able to see that the angle B here is also equal to angle Q. B in the smaller triangle is equal to angle Q. Then we have an angle that is left. Right, so we have the angle C1, which is the third one we've not touched in the smaller triangle. So the angle C1 is equal to, right, if the angle C1 is actually checked very carefully, it is actually the same as 180 degrees minus 2x. It is 180 degrees minus 2x. So if the angle C1 is 180 degrees minus 2x, what then do we need here? So it would be the same as equal to what angle in the bigger triangle? It would actually be the same as this angle here, BRQ, because this is X and that is X in the bigger triangle. So this is like 180 degrees minus 2x, so that it is also the same as the angle BRQ. And why is this the case? This is true because of the sum of angles of triangle. Therefore, the triangle ABC. Okay, we can write them in that particular order, but I would feel that I would rather like to write it in a way that is going to produce the BA. Doesn't really matter. So if you then say, therefore, the triangle. Okay, if you write like BAC, it's similar to triangle. Right, so what is the angle B in BAC equal to in the triangle QBR? In the triangle QBR, we are able to see that the angle B in the smaller triangle is equal to what in the bigger triangle? Right, we're able to see, therefore, that the angle B here, we said that the angle B is equal to the angle A. So that now, if you're able to see that in the smaller triangle, okay, right, the angle B in the smaller triangle BAC would be equal to the angle Q. Right, the angle B is actually equal to the angle Q. So the angle B in the smaller triangle equals the angle Q in the bigger triangle, but also the angle A1, we've already seen that it is actually equal to the angle B. The angle A1, it is actually equal to the angle B, but also the angle C is equal to, like, C1 is like the middle angle R. So in other words, so C is equal to the angle R there, like that. So now with that, because C1 is that, so we've already said the angle C1 is equal to the angle R there, which is the angle BRQ. So, and this is true because of the following, and this is angle, angle, angle. This is angle, angle, angle. Right, so now what then are we able to achieve out of this? Okay, what we're able to achieve out of this is that therefore you can be able to mark them green. So you have the BA here, the first two like that. So let's check what this is gonna give us. So it actually is giving us BA over QB. Right, so we have BA over QB. So if you have BA over QB, it must be the same as. Let us check this. So you can be able to see that, for instance, if you take in line with this, so you can be able to see the BC, and then it's gonna go with this one. Let us check that one, please. We're checking this. So you'd have BC, okay, over QR. Awesome, awesome. And then we have the following. Okay, yeah, we're already there. Which is BA over the QB. So we wrote QB there, but you can write it as BQ. Can write this one as actually BQ, like this. And then this is BC over QR. Any question on this one? Any question on this one here?
No,
No
no
question.
questions.
Okay. Yeah, so yeah, we're saying really we're attempting to prove this in two ways. First, we used the proportionality theorem to actually achieve the result. Why was the proportionality theorem relevant here? Because you already have a triangle that had a line parallel to one side. Proportionality was immediate. But also this one here. We have the next point. We have the next question. Right, let's look at the next question. Right, the next question is this one here. In the diagram, O is the center of the circle. So use the diagram above to prove the theorem, which states that the angle subtended by a chord at the center of the circle is equal to twice the angle subtended by the same chord at the circumference of the circle. So we attempt to prove this particular result, and it is a very, very simple one, and we spend a bit more time trying to establish this particular fact, and we actually are good at proving this one, and we enjoy it. Let's get started with this. So to prove this one, you need to prove that the angle TOP. We need to prove that the angle TOP is actually 2 times the angle TKP. TOP is 2 times the angle TKP. Construction. You need to draw KO and produce. You need to draw KO and produce. So that's what we're going to do. Draw KO and produce. Okay? So we need to draw KO and produce. So we do this. Right, we draw a KO and produce like that. And then we can call this one 1, 2, and then we can call this one 1, 2. What is the angle O1? What is the angle O1? It's actually K1 plus the angle T. O1 is actually K1 plus the angle T. Why is this the case? We're back to grade 10 because it's like an exterior angle of a triangle, which is the sum of the interior opposite angles. And therefore, we say here it is exterior angle of triangle. Exterior angle of triangle equals the sum of the interior opposite angles. But also, we have that the angle K1. The angle K1 is actually equal to the angle T. Why is this the case? Right, the angle K1 is equal to the angle T. Why is this the case? Right, and these are angles opposite. Angles opposite equal. Angles opposite equal size. Angles opposite equal size. So that the K1 equals T. Next, we're able to know that the angle O1, right, is therefore equal to, okay, so it's K1 plus the T is K1, which is 2K1. Next, we have that the angle O2 is equal to what? The angle O2 is K2. It's the angle K2 plus the angle P. Why? Why is the angle K2, rather O2, equal to K2 plus P, exterior angle of triangle from grade 10. Exterior angle of triangle. But K2 is equal to angle P. Why is this the case? K2 is equal to angle P. Why is this the case? These are angles opposite equal size. Angles opposite equal size. Take a look at this and make sure you understand this. But these are angles opposite equal sides. Right, so this means that K2 is equals to angle P, and these are angles opposite equal sides. Angles opposite equal sides. And therefore, now we have that the angle O2 is therefore equal to K2 plus K2, which is 2K2. Right, like that. So what exactly is the meaning of this? So at this point, we can be able to add the fact that the angles have the following relation. We have the following addition to do. The angle O1 plus the angle O2. Okay, so the angle O1 is 2K1. Right, so the angle O1 is 2 angle K1. The angle O2 is 2 times angle K2. Angle O1 plus O2 is 2 times, right, so it's 2 times K1, K2. So the angle O1 is plus O2 is 2 times K1, K2. 2 times K1, K2. Therefore, this means that the angle TOP, which is O1, O2, is 2 times TKP, like this. So the angle TOP is 2 times TKP. Right, because we have already seen, therefore, that the angle O1 plus O2 is 2 times the K1, K2 in parentheses, and therefore the angle TOP is equal to 2 times the angle TKP. Right, any question on this one? Angle at center equals twice angle at circumference theorem. Anything to add, remove, any comment on this one now?
No, thank you, sir.
Okay, good. We move on. Okay, you need to practice this one because these are like past exam questions. You need to practice this. Make sure that you like repeat. When you watch the video, it should not just be a question of just seeing the video, but it should be a question of really saying, at the end of watching, you must be able to do it yourself on your own without even watching the answer or copying the answer from anywhere, to make sure, because it's one of those theorems you really can expect in the exam. Okay, the next one in the diagram. O is the center of the circle, and ABCD is a cyclic quadrilateral. So we have that O is the center of the circle, ABCD is a cyclic quadrilateral, OB and OD are drawn. So we have OB and OD are drawn. If the angle O1 is 4x plus 100 degrees, let us put it in the diagram because the examiner did not do it for us. So we have the angle O1, what is it? 4x plus 100 degrees. The size of the angle C, it's x plus 34 degrees, like so. Calculate, giving reasons, the size of x. If they've given us 4x plus 100 degrees, x plus 34 degrees, what is the size of x? We want to find the value of x. Now the question is, how do we even start doing this here? Right, so it's an awesome one. We can start as follows and make the following observation at this point. So we take note of the fact that the angle O1, is 2 times angle A. Why is this the case? Angle O1 is 2 times angle A because angle at center equals 2 times angle at circumference. Angle at center is 2 times angle at circumference. Right, but the angle O1 is 4x plus 100 degrees, which is 2 times angle A. Why is this the case? Because the angle O1 here is actually 4x plus 100 degrees. Why is this the case? Given, divide both left and right by 2 so that the angle A becomes 4x plus 100 degrees. You divide by 2. What is 4x plus 100 degrees? It's actually 2x plus 50 degrees. Why is this the case? So now we're able to see that this one is 2x plus 50 degrees, and that is the size of this angle there. What then is the numerical value of x? Right, so which means therefore you have 2x plus 50 degrees. 2x plus 50 degrees plus, so you're adding also the x, you're adding also the x and 34. You're adding also the x and 34 degrees. Why is this the case? And if you add all these here, you get 180 degrees. Why is this the case? These are opposite angles of cyclic quad. Opposite angles of cyclic quad. Okay, let us add this because now you're adding the A and the C, opposite angles of a cyclic quad. When you add them up, this has 1, 2, 3, 4 vertices, and therefore it's a cyclic quadrilateral. Quad means 4 vertices. And now the vertices lie on the circumference. Since the vertices lie on the circumference, we have what we call a cyclic quadrilateral. And therefore we have x plus, rather 2x plus x, which gives us 3x, equals the 50 degrees plus 34 degrees give us 84 degrees, and this is 180 degrees minus 84 degrees. 3x equals, what is 180 minus 84? Right, 180 minus 34 is actually a 96. And then now we have 3x equals 96 degrees. You divide by 3, you divide by 3. And this means that x, what is 96 divided by 3? 32. 32 degrees. 32 degrees. So now x equals 32 degrees. X equals 32 degrees. So we have to calculate the size of x, and x is 32 degrees. X equals 32 degrees. Any question? No. But yeah, there's a couple of other ways to do this particular question. But yeah, this is most certainly one way to do that. Another way to do this is to also say 360 minus this one. 360 minus 1. You can say 360 minus this, and then you get this angle here, and this is the angle at center is twice this. So you can also use angle at center is twice this by using the theorem that is like this. Right, if this is the center, then you have this angle here, which is twice that one. Right, so because the angle at center is, this at center is 2 times that, but you can have this one here. And this angle here, you can say 360 degrees. Right, you can say 360 degrees minus the angle that's given there. So if you then say that, 360 minus 4x plus 100 degrees, like this. So if this is the case, 360 minus this. Okay, so yeah, we get the answer. We get the answer. Right, so we're good. So we're good. We're good. All right, yeah, but x becomes 32 because 360 minus that, and then you say this one here equals twice this, and then you get the same answer, x equals 32 degrees. Any question there, Noah?
No questions.
No question. Right, let's move to the next point. I can see that we're really a little bit, we are finishing our discussion, please. Right, as said already, we can do this one. You can do this one. In the diagram, O is the center of the larger circle. O becomes the center of the larger circle. OB is the diameter of the smaller circle, with OB is the diameter of the smaller circle. Okay, if OB is the diameter of the smaller circle, what do we know? It subtends an angle of what? Its circumference, it subtends an angle of 90 degrees in the circumference of the circle. Now, chord AB of the larger circle intersects the smaller circle at M and B. Right, so you have M and B intersection. Write down the size of the angle OMB. What is the size of the angle OMB? Obvious, yeah?
90.
90. Why? Okay, the examiner was just implicit in that one.
Angle in a semicircle.
Angle in semicircle. Well done. I'm happy that you're able to see that one. Angle in semicircle. So now we have that the angle OMB is equal to 90 degrees, which is an angle in semicircle. Next point. Right, if you have AB is the square root of 300. AB is actually the square root of 300. Right, and OM OM is 5. OM is 5 like this. 5 units. What then do we need to do here? Calculate, giving reasons, the length of OB. What is the length of OB? We want to find the length of OB because this one you already know is 90 degrees. We just need to find the length of OB. Very, very obvious. But first things first, we need to find the length of OB, we must find the length of MB. What is actually the length of MB? Right, so how do we find the length of MB? Right, so we know very well that MB is equal to what?
5 square root 3.
Yes, it will be that because you know
5,
this one is
5
3.
root 3.
Yeah, 5 is going to be here. I get it. Years you have 5 is going to 3 there. Okay, that's brilliant stuff. That's brilliant stuff. Right. So in other words, we want to find MB. So we know that MB, right? I mean MB equals 1/2. Right. So we're able to see that MB is AB out of 2. So if you take AB and divide by 2, you get like half of it, which is the MB. Why? Because of the line from center, perpendicular to chord. Line from center perpendicular to chord. So that now you have the MB is actually the whole of AB you divide it by 2. The whole of AB divided by 2. So that in the end, what you then getting here is that you'd have therefore that MB is AB. What is AB? AB is the square root of 300. Right, the square root of 300, which you divide by 2. What is 300? Is 3 times 100. You divide by 2, which is the square root of 3, the square root of 100. You divide by 2. The square root of 100 is what? 10. Square root of 3 divided by 2, which is 5 to the square root of 3. 5 to the square root of 3. 5 to the square root of 3. Right, so as you're saying, it's 5 to the square root of 3 there. So that's good. So this MB is 5 to the square root of 3. We're asking the question, then what is OB? What is then OB? Because you've already got like 2 sides of the triangle. 2 sides of the triangle OMB. So in other words, we are dealing with in triangle OMB. What is then the OB there? So we can be able to see that OB squared is equal to OB squared is what? Is OM squared. OM squared plus MB squared. Why? Pythagoras. Pythagoras. Right, so now, which is OB? OB squared. What is OM? OM is 5. So you put a 5 squared there. What is MB? MB is 5 to the square root of 3. And you square this. And if you have everything here, this is actually OB squared. The 5 squared is 25. And here it's 5 squared, which is 25 by 3, which is 75. 25 plus 75 is 100. Which means OB is the square root. Is the square root of 100. And OB is 10 units. OB is what? It's actually 10 units. So we're to calculate the length of OB, which is actually 10 units. Any question on this one, Neo?
No.
No question. Right. We have come to the end of our discussion for today, and we'll keep in touch most certainly for more practice. But we're gonna give you a small exercise. Right. Here is the exercise. Obviously, I mean, you don't need to copy it down because it's going to be part of the recording. We're going to send you the recording. But now in the diagram, ABCD is a parallelogram. So you have that ABCD is a parallelogram with AB equals 14. So you have AB is 14 units. AD is produced to E. So you have that AD is produced to E such that AD to DE. Right, so that AD to DE is 4:3. EB intersects DC in F. You have that obviously your EB here, which means that if you have EB, it intersects DC in F. EB is 21 units. So you have that your EB is 21 units. Calculate given reasons the length of FB, like Facebook, right? So we want to find the length of FB, right? We want to find the length of FB. Prove with reasons that the triangle EDF, is similar to the triangle EAB, So you're going to obviously attempt that one as an exercise. Calculate, giving, rather with reasons, the length of FC. You need the length of FC. You need to calculate giving reasons, right? So obviously it's just the proportionality and similarity, or similarity and proportionality results, and the what you call the proportionality theorem that we spoke about earlier on being used here. And this is awesome news. I think that it is some excellent time to call it a very good afternoon. We started at what time, by the way? We forgot. We started like 12.
12.
Just 12, and then now it's 9 past 2 in the afternoon. So thanks so much for your time and attention. It was awesome having this discussion. We keep in touch. Once again, I can always send questions during the course of the week. But for now, it was awesome having this discussion. Thanks a lot, Noor, and take care. Have a good afternoon, and goodbye.
Goodbye, sir. Thank you.
Goodbye, Noor.